Hello everyone, my name is Christian and today we will talk about bicycle speeds and gear ratios. I think everyone has heard terms like single speed bicycle or 21 speed bicycle, but what do they actually mean? Are all 21 speed bikes the same when it comes to how they convert the rider's feet movement into bike travel? Let's start with a simple concept. When you walk, your foot is pushing the ground backwards and, as a result, your body is moving forward. Then, the foot is lifted and moved to a new forward position. Setting aside the mechanics, we can imagine each foot sliding on the ground at the speed of walking. For example, if you are traveling 1 meter every second, your speed is 1 meter per second. When riding a bicycle, your feet are moving in a circular motion. Their movement is transferred to the ground through the bicycle's gear train and rear wheel. Is there a way to compare walking with biking? Yes, if we are considering the linear speed at which the feet are moving in their circular motion. For example, let's say the crank arms and the feet rotate a full turn in 1 second. The crank arm length is c. Then the linear distance traveled is LF equals 2 times pi times c, and the linear speed is Vf equals 2 times pi times c divided by 1 second. A common crank arm length is 170 millimeters or 0.17 meters. In that case, the distance traveled at each rotation is LF equals 2 times 3.14 times 0.17 meters equals 1.07 meters, and the linear speed is Vf equals 1.07 meters per second. We see that the two speeds of 1 meter per second and 1.07 meters per second are comparable. However, the bicycle will move at a different speed than Vf. In order to calculate the latter, we need to know a few more things. From the crank arms, the movement is transmitted to the rear wheel through a chainring, which rotates at the same speed as the crank arms, a chain, and a cog that rotates together with the rear wheel. The wheel pushes the ground backwards and the bike moves forward. To determine how much the bike moves forward, we need to look at how much a point on the periphery of the wheel moves in a straight line at every turn of the crank. We will use the following notations. C. Crank arm length. Z1. Chainring's number of teeth. Z2. Cog's number of teeth. R. Wheel radius. D. Wheel diameter. As the chainring rotates, the upper stretch of the chain moves forward. The chain rollers engage with the chainring's teeth. For every rotation of the chainring, the chain advances a number of links equal to Z1. At the other end of the stretch, the chain moves by Z1 links and pulls the periphery of the cog. But because the cog has a different number of teeth, Z2, it will rotate faster or slower than the chainring. For example, if the chainring has 40 teeth and the cog has 20 teeth, for every rotation of the chainring, the cog will rotate 2 times in order to match the 40 links pulled by the chainring. The number I equals Z2 divided by Z1 is known in the industry as the gear ratio. It is actually the rotational speed of the first, or driving, gear divided by the rotational speed of the second, or driven, gear. I equals omega 1 divided by omega 2, or omega 2 equals omega 1 divided by I. For every full turn of the driving gear, the driven gear will rotate 1 divided by I, or Z1 divided by Z2 turns. The point on the periphery of the wheel will then move a distance equal to LW equals 2 times pi times R divided by I, or LW equals 2 times pi times R times Z1 divided by Z2. To continue our example, if the wheel size is 26 inches, the radius is 13 inches or about 330 millimeters. Therefore, LW equals 2 times 3.14 times 0.33 times 40 divided by 20 equals 4.14 meters, and the bicycle's speed is 4.14 meters per second. With all this information, we can go ahead and define the total transmission ratio as K equals LF divided by LW, or K equals 2 times pi times C divided by 2 times pi times R times Z1 divided by Z2 in parentheses, or K equals C divided by R times Z2 divided by Z1, or K equals 2 times C divided by D times Z2 divided by Z1. With the numbers above, K equals 170 divided by 330 times 20 divided by 40 equals 0.258. This number is the ratio between the input speed, the foot's linear speed, and the output speed, the bicycle's speed. Although mathematically correct, this ratio is counterintuitive. At the same foot speed, a higher ratio means a lower bike speed, and a lower ratio means a higher bike speed. This is in contradiction with the way speeds are numbered on shifters, where a higher number means a higher speed and vice versa. To go around this issue, we will make use of the inverse ratio, T equals 1 divided by K, or T equals R divided by C times Z1 divided by Z2, or T equals D divided by 2 divided by C times Z1 divided by Z2. With the above numbers, T equals 3.882. It means that for every meter of foot travel, the bike will move 3.882 meters forward on the road. A measure that is alternatively used is the distance traveled by the bike at every rotation of the crank wheel. While that is useful in some cases, it is not a full measure of the transmission ratio because it doesn't include the crank arm length. Imagine having a bike with 175 mm crank arms and replacing those with 152 mm arms. While you're traveling the same distance for every rotation, will your experience be the same? Armed with this knowledge, let's put together a calculation table and use it for a popular configuration found on many mountain bikes. In this configuration, C equals 175 millimeters, D equals 29 inches or 736.6 millimeters, Z1 equals 28, 38, and 48, 3 chainrings, and Z2 equals 28, 24, 22, 20, 18, 16, and 14, 7 cogs. The chainrings are listed from the smallest one to the largest one, and the cogs are listed from the largest one to the smallest one in order to match with the numbering on the left and right shifters respectively. This table calculates the transmission ratio for all 21 possible combinations of chainrings and cogs. The ratio varies between 2.10 lowest and 7.22 highest, as shown in the all column. In the adjacent increase column, the percentage increase when going from one cog to the next one is shown. For the first cog, however, the increase when going from one chainring to the next one is shown. However, combinations that place the chain at an extreme angle relative to the center plane of the bike should be avoided. Although this is not clearly defined, based on my experience, I would avoid the combinations between the smallest chainring and the two smallest cogs, and between the largest chainring and the largest cog. The middle chainring can be used with all cogs. The allowable combinations are shown in the allowed column. In the sorted column, they are placed in ascending order. The second increase column shows the percentage increase of each ratio relative to the previous one. Looking at that, what is a meaningful increase? In other words, how easy would you feel the difference in pedaling if you go from one ratio to the next one? It's hard to give an exact answer, but I believe 5% is a good arbitrary number. As a side observation, if two adjacent increases are both less than 5%, but together they are higher than 5%, that should be counted as one meaningful increase. So how can this table be used in a practical way? First, let's look at the smallest and largest ratios. The smallest ratio will tell you how easy you will go on steep slopes. The smaller the ratio, the higher the force that pushes you ahead will be. The largest ratio will tell you how fast the bike will go. The larger the ratio, the faster the speed at which you can ride the bike. Second, you will get an idea of how many distinct speeds are available. Despite a bike being advertised as a 21 speed, you will understand that the number of distinct speeds is lower, 13 in this case. Third, you will be able to compare different bikes from this point of view only. There are many other factors that contribute to the feel and performance of a bike. Bike weight and geometry, tire tread, width and pressure, aerodynamic resistance, suspension type, gear train efficiency and lubrication, rider weight, rider fit, and so on. I hope this video will help you make a more informed decision when buying a bike and provide you with a consistent way of looking at speeds and ratios. Thank you for watching this video. Please press the like button if you found it useful and subscribe to my new channel, The 10 Minute Point, for future informational videos. Have a great day!